video, we are going to be discussing the topic of paramagnetism, which is the other form of magnetism we are going to be discussing in this course after diamagnetism. Now, unlike diamagnetism, the materials which are said to be paramagnetic actually do possess an intrinsic magnetic dipole moment. However, the reason that paramagnetic materials are not permanent magnets, unlike ferromagnets, is because of the fact that the orientation of the magnets is not the same. And we actually do have to go into statistical physics just a little bit to examine how the magnetic susceptibility actually depends on the temperature. And what you find is that for very low temperatures, you get that these materials become magnetic because it's energetically favorable to do so. So let's go ahead and jump right into this derivation. So, as I said, paramagnetic materials contain atoms which do have an intrinsic dipole moment. Now, with diamagnetism, the electrons in the outer shells of these atoms have a net zero angular momentum because they are full. And this is due to the quantum mechanical effect of spins being added to certain levels, and for a fully complete outer shell, you have that L is equal to 0, and therefore the magnetic dipole moment of the atoms, the intrinsic magnetic dipole moment, is also 0, because of course magnetic dipole moment and angular momentum are intrinsically linked. And the only way in which you actually get a magnetic response from these materials is by essentially forcing them to precess on their orbits. And that is essentially what causes diamagnetism, and it is a very weak effect. Paramagnetism is kind of like what occurs in all other materials. So with paramagnetism, the angular momentum is not equal to 0, and therefore you have that the magnetic dipole moment is also non-zero. And what's actually going on the atomic level is that for a certain orbital, so what I'm going to do is I'm just going to draw the spins, the orientation of the spins in certain orbitals, and each box here represents an orbital. You find that the electrons actually occupy different orbitals, and this is due to what's known as Hund's rule in chemistry. And because of course you have two spin ups, this of course sums together, and obviously this isn't going to cancel out. Whereas with the diamagnetic case, because of course it was fully filled, then you essentially had every single spin up electron cancelling with every single spin down electron to produce 0 net angular momentum. But with the paramagnetic case, this has a non-zero angular momentum and therefore a non-zero dipole moment. But I did say that at room temperature, then these materials are not actually magnetic. And that is because all of the dipole moments are essentially oriented in random directions. So if we were to draw out just kind of maybe like a cross-section of the paramagnetic material, then if we just draw all these dipole moments, then we actually find that the dipole moments are completely randomly aligned. And so as a result, you don't get any magnetic effect at all, because of course there is no net dipole moment in any given direction, since the direction is completely random. And this is what happens at high temperature. And because of course temperature is the random motion of all of these atoms, then even if we apply a magnetic field, B right here, you still find that these dipole moments are not going to stay still. They're just going to shift around. And so they're still going to not produce any net magnetic response or magnetization within this material. But what happens when we lower the temperature? Well, what we actually find is that the magnetic dipole moments of all the atoms actually start to align with each other. And this is kind of what produces the magnetic response. So we apply our field right here, and we find that the magnetic dipole moments tend to align with the field, the externally applied magnetic field, and this is what produces a macroscopic magnetization. And this is what's going on at low temperature. So clearly there's some kind of energy change right here that's taking place. In this situation with high temperature, because of course temperature and energy are essentially measuring the same thing, then the thermal energy is obviously way higher than the energy in which it takes to reorient these dipoles. Whereas in this regime, you actually find that the energy in which it takes to reorient the dipoles is actually more than the thermal energy. And so as a result, it's energetically favorable for the dipoles to have this kind of configuration where they are all aligned. So what is this magnetic energy? Well, we said that the magnetic torque which is experienced by a dipole due to an external field is equal to the magnetic dipole moment M cross-producted with B right here. And to get the potential energy, what you actually have to do is you have to do an integral of the torque over the angle right here. So if you imagine a thing that's spinning, it of course takes energy to cause it to kind of spin around the pivot point. And you can kind of think of this torque as very much like the force. And so this equation is essentially a bit like force times distance, except you have torque and angular distance. So it's the angular equivalent. Now, of course, many times we say we can express any cross product as the magnitude times sine theta. The magnitude's right there. And so substituting this in, we're going to get the integral of mb sine theta d theta right here. And for now, we're not going to worry too much about what the limits are, because when we do this integral, we actually get minus mb cos theta. And also you can express this as minus m dot b in vector terms. When you take the dot product, you are essentially looking at how much in common the angles are, and so therefore you get this cos theta. So this right here is telling us that there is an angular dependence of the energy on the dipole given a external magnetic field. And that's just like what we said. We said that obviously for the configuration where the magnetic dipole is parallel to the field right here, so you have B and M right here, then obviously that is a lower energy state than if the magnetic dipole moment was in this direction and was anti-parallel the field. This is at a higher energy state, and this orientation right here is when theta is equal to 180 degrees or pi radians. But when they're parallel, then obviously the angle is going to be 0 right here. So this is our energy, our potential energy of the dipole as a function of the angle it makes with the field. Now, we said before that the energy of a dipole that's kind of just moving around is related to the temperature. And this is where this very small piece of statistical physics is going to come in. Because in statistical physics, we showed that the Boltzmann distribution gives us the probability of a system of particles being in a certain state, a certain energy state. And so the Boltzmann distribution, in terms of the probability density function, given by this P right here, we said was equal to 1 divided by what's known as the partition function. And don't worry about that too much for now. We don't actually have to understand what it is. We just need to know that it essentially normalizes the Boltzmann probability distribution. Multiplied by this exponential, and this is the key thing right here, because of course we find that higher energy levels are exponentially less likely to occur. So what this is essentially saying is that any particle is more likely to be found at lower energies, because if we were to draw a very simple graph right here of energy and this probability distribution, we find that we get a curve that looks a little bit like this. So further up the energy scale we go, the less likely the particles are to be found right here. So that is just our small piece of statistical physics that we're going to be borrowing, and we're going to use this to help us calculate our paramagnetism relationships. Now, we can substitute in, rather than E, we can actually substitute this to get this as a function of the angle, because of course we said that the angle is intrinsically linked to the potential energy. And this E right here, we can just substitute in the potential energy U right here. So the probability, but this time as a function of the angle right here, is going to be 1 divided by Z times E to the minus, and instead of E, we can just swap this out with U. And this is, of course, minus mb cos theta. So we're going to get e to the minus mb cos theta. So this minus sign is going to go. And we're going to get e to the mb cos theta divided by kbt right here. So this is our probability density function as a function of the angle which the dipoles make with the field. So that's fine. But we need to do something about this z right here. So a key property of a probability density function is if you integrate it over all space, essentially, whatever geometry you're working with, then you must get that this is equal to 1. So for every single possible value that theta can take, then this must sum up to 1. The area underneath a probability distribution function must equal 1 because everything must be possible. And that is a key property of the probability density functions. They must have an area when integrated over all space equal to 1. But we are actually in 3 dimensions right here. And instead of just integrating over theta, we actually have to integrate over the azimuthal coordinate phi as well. So if we kind of think about why that needs to happen, we of course have our dipole right here, our magnetic dipole, and it's got a field applied. Now, as well as being able to rotate just in this plane, it might also be able to kind of poke outwards as well. And so therefore we have to take into account the azimuthal angle phi as well as just theta. And the way in which we do that is rather than normalizing over just the theta angles, we actually normalize over what's known as the solid angle, omega, right here. And so what d omega is for a sphere, this is equal to sine theta d theta d phi. And so this is essentially an element of solid angle right here. So it's not a surface area element, just to make that distinction. This is just a solid angle. And this quantity omega is measured in steradians, and you find that there are 4 pi steradians in an entire sphere. And it's kind of analogous to how there are 2 pi radians in a circle in 2 dimensions. There are 4 pi steradians in a sphere in 3 dimensions right here. So this is kind of our normalization condition. We must find that the integral over all solid angle is equal to 1. So let's go ahead and normalize this equation by simply putting this underneath the integral. So we're going to get the integral of 1 over z e to the mb cos theta over kbt, and this is going to be d omega, and we said that this must be equal to 1 in order for this to be a probability density function. So let's just go ahead and rearrange this a little bit. So we're going to find that this z is going to be equal to, it's going to be a double integral because of course we have a theta and a phi, and the phi component is going to be between 0 and 2 pi because that is the entire range of phi, and the theta component is going to be between 0 and pi right here. And we're going to get this exponential, and this is going to be multiplied by sine theta because of course we had a factor of sine theta in this d omega. There's our d theta d phi right here. Now, of course, our probability density function has no phi dependence at all. It doesn't matter what angle phi you have, the potential energy of the dipole is going to be exactly the same in either case. So what we can do is we can just bring the phi part of the integral separate from the theta part right here. So we have the integral 0 to 2 pi d phi, because there is no phi dependence whatsoever, multiplied by, so of course this component is just going to integrate to give 2 pi, and this is kind of what we found a lot of the times before in this course. Because you have no phi dependence, you essentially just get a factor of 2 pi out the front. But of course, this does account for the fact that it's in 3D and you have to integrate over all possible phi angles, even though there is no phi dependence. And this is all going to be multiplied by this right here. Now we're going to do our usual trick of making a u substitution with these integrals. And of course, we have to be a little bit careful about what we're going to substitute. And in this case, our ideal u substitution is that u is equal to cos theta right here. And so as a result, when we take a derivative, we get du by d theta is equal to minus sine theta. And therefore, we get that minus du is equal to sine theta d theta right here. So now just rescaling our integral and making it all in terms of u, we get that z is equal to 2 pi. And of course, our limits are going to change. So we're going to get 1 to minus 1 right here, because of course cos of 0 is 1 and cos of pi is minus 1. And we are going to get e to the mbu over kbt. And then we have our sine theta d theta, but we've found that that just substitutes to minus du right here. And just like we can often do with these integrals, we can just go ahead and get rid of this minus sign in exchange for reversing the limits right here. So now we just simply have a fairly straightforward exponential integral between two limits. And so let's go ahead and integrate this. So we're going to get z is equal to 2 pi, and for our factor, we're going to get a factor of kbt divided by mb, and we're going to get our exponential e to the mbu over kbt, and our limits are between -1 and 1 right here. So let's go ahead and substitute in our u values. So we're going to get e to the mbu over kbt for our top limit, and this is going to be subtracted from e to the mbu is -1 in this case, so we're going to get a minus sign over kbt. Now, whenever you have e to the power of something minus e to the minus the same thing, this is actually a hyperbolic function right here. And the hyperbolic function in question is the sine function. And so what we can do is we can substitute in a sine function right here. So just to reiterate, sine x is equal to 1/2 e to the x minus e to the minus x right here. And this is exactly what we've got. We have e to the something minus e to the minus the same thing. So substituting this in, we're going to get 2 pi kbt over mb. Now we don't have a factor of 2 here, so therefore we need to double it. And so we're going to get 2 times sine mb over kbt right here. And these 2's are just going to combine to make a 4. So we're going to get this right here. And so this is our value for z. So let's go ahead and substitute this back into our probability density function. So we have that p of theta is equal to 1 divided by z, e to the minus mb cos theta divided by kbt. And so substituting in this value for z, we get this. So there we go. This is our probability distribution function, and it tells us how likely we are to find a magnetic dipole at a given angle theta to the magnetic field right here. And it's quite a complicated function because we have this sine in the denominator and then we just have this exponential in the numerator right here. But let's not worry about that. Now that we have this, we can actually use this to calculate the overall magnetization. Now, how on earth are we going to do that? Well, the overall magnetization, M right here, is simply equal to the number of magnetic dipoles per unit volume. And we can actually take an average of the magnetic dipole moment over the entire solid. And this is how we are going to get our value for the magnetization right here, is by taking an average value and then just multiplying it by the number density. Now let's go ahead and say that our field right here, our B field, is in the Z direction as we normally do. Then how is this going to affect things? Well, the only relevant magnetization that we're going to get if we orient our B field in the Z direction is also only going to be that in the Z direction. But of course, we're kind of working in spherical coordinates with our dipoles right here. And so because of that, we actually only want to be taking into account the Z component of the dipoles right here. So we can essentially rewrite this as mz, so just kind of turning this into a scalar equation, is going to be equal to n times the average magnetic dipole moment, but only in the Z direction right here. So there we go. Let's go ahead and try and calculate this. Now, whenever we have an average right here, the way in which we take an average is you actually integrate over the entire solid, but you weight it by the probability density function. It's a little bit like calculating the expectation value in discrete random variables in statistics. You essentially multiply the frequency density by whatever sort of ordered variable you have. But of course, we're in the continuous case, and so rather than summing up, we actually use integration. And so to calculate the average value of the magnetic dipole moment, we do an integral, and this integral is yet again going to be over the entire domain in which the dipoles can point, and that is going to be over the solid angle. And this is going to be our quantity, mz, right here, times the probability distribution function, which we said was p of theta, and this is going to be over omega, like we said. So how do we get just the z component? Well, in spherical coordinates, to get the z component, we simply get the overall magnitude, but multiply it by cos theta. And this is basically coming from the fact that z is equal to r cos theta. So we're going to get a double integral because, of course, omega has a d theta d phi in, and we're going to get our phi going from 0 to 2 pi, and we're going to get our theta going between 0 and pi. And so rather than mz, we're just going to get m cos theta, and we're going to get our probability distribution function, and we're going to get a factor of sine theta coming from the d omega times d theta d phi right here. Now, just like before, there's no phi dependence anywhere in the integral, so we're going to get just a factor of 2 pi, just like we had before. So let's go ahead and now write in all of the terms. So we're now going to substitute in what p of theta is, and this is going to get a little bit crazy, but it's essentially just plugging everything in and then just doing the calculation. So we're going to get 2 pi times this m right here. This is going to be a constant. And for our prefactor for p of theta, we are going to get all of this right here. So what are we going to end up in our integral? We're going to get the integral between 0 and pi. We've got a cos theta and we've got a sine theta. And in our p of theta, we had a factor of e to the mb cos theta divided by kbt. This is all going to be over theta right here, integrated with respect to theta. This is a bit of a load right here, but we can make a few little simplifications. So the pi's are going to cancel, and 2 divided by 4 is just going to give a factor of 2 right here. And the m is going to double up right there. So our prefactor is going to be just all of that right there. So the integral cos theta sine theta e to the something times cos theta d theta. How are we going to tackle that? Well, funnily enough, we're actually going to still use the same thing as before. We are going to let u equal cos theta, just like before, and we're going to get that du from that is equal to minus sine theta d theta right here. And so this we can go ahead and use to rescale our integral. And so rather than between 0 and pi, yet again, we're just going to get it between 1 and minus 1 right here. And so what do we have inside our integral? Well, we have a cos theta, and therefore that is just going to be u. We have a sine theta d theta, which we said was a minus du, which I'm just going to put right here. And this is going to be multiplied by this exponential, e to the mb over kbt, and rather than cos theta, we are just going to write u, just kind of a little bit like what we did before. And this integral right here, we can evaluate using integration by parts. Now, the way in which you can kind of quickly do integration by parts is by deciding which part you're going to differentiate and which part you're going to integrate, which is going to be those two respectively right there. Often the way in which we can kind of label this is we can say that the part which we're going to differentiate is going to be equal to u, which in this case happens to be u already, so we might as well just stick with u. And essentially you just keep differentiating this until you get 0. So u dash is 1, u double dash is equal to 0. But what is our v derivative? Well, that's going to be the other part, v dash, and that is going to be equal to e to the mb over kbt times u. Now, instead of differentiating, we actually integrate. So we get v, the integral of v is going to be kt over mb times the exponential. And we have to integrate one more time. So the integral of v is going to be this same factor again. So we're going to get this factor squared times the exponential right here. And you actually link up the diagonals right here. So this gets multiplied by this, and this gets multiplied by this. And there we go. There's a kind of quick-ish way of doing integration by parts. And so let's go ahead and substitute all this in for our integral right here. So we're going to get that the average magnetic dipole moment in the z direction is equal to all of these prefactors multiplied by. So what's our first term going to be? It's going to be these two factors right here. So we're going to get, all right, that's our first term. And then we actually have to subtract the second term because these signs actually alternate. And so you have u dash, which is 1. And so you have the integral of multiplied by the integral of v, which is this right here. And all of this is going to be evaluated between -1 and 1. And one thing I didn't actually mention was that I, in fact, did exactly what I did by reversing the limits and just removing the minus sign. So we're going to end up with a massive expression. So this is going to have 4 terms in when we substitute in 1 and -1 for these u's right here. So I'm going to go ahead and skip to when these are all substituted in. And there we go. And we have a massive, massive expression that looks pretty horrific, but thankfully, a lot of cancellations will happen right here. And the reason why so many cancellations will happen is because, again, we can use hyperbolic identities. Now, we have 2 terms which have the factor kt over mb. This term right here and this term right here. And the consequences of this is that these 2 terms you can actually double up using a hyperbolic function. So we have an e to the plus something minus e to the minus something with the same prefactor on the end. And what this is going to lead to is a cosh function. And just to remind you, cosh x is equal to 1/2 in brackets e to the x plus e to the minus x right here. And so what we can do for these 2 terms right here, we can substitute this in for this prefactor times 2 cosh of the argument in the exponential right here. So that's our first term. But what about a second term? Well, we have a similar situation, but this time the factor outside is kbt divided by mb squared right here. And this happened when we integrated by parts. So let's just go ahead and see what we've got. We've got a minus kbt over mb squared times e to the mb over kbt. But that's a minus, and then we have a minus, that's going to cause a plus. And the positive term is going to be the one with the negative exponential. And this naturally on its own isn't a hyperbolic identity, but because you have 2 terms, one of which is added and one of which is subtracted, each of which having differing signs in the exponential, this still equates to a sign, except you will get that this is subtracted. So we're going to end up with this right here. So this is looking like an absolute mess still, but thankfully we can actually simplify this quite substantially more. Now we can make use of a couple more hyperbolic identities, and what we notice is that we have a shine function in the prefactor outside this massive brackets right here, and then we have 2 hyperbolic functions, one in each term inside the bracket right here. So that essentially means that when we multiply this out, we're going to end up with cosh divided by shine of exactly the same thing. Now, these identities work in a very similar way to the normal trig identities. And what you actually find is that because sine divided by cos is normally tan, then cos divided by sine, and this is in normal trig identities, is cotan. But of course, this is hyperbolic. So it's not going to be cotan, it's going to be the hyperbolic version of cotan, which is coth. And coth x is defined as cosh x divided by shine x right here. And it's very similar to how cot x is cos x divided by sin x, and this is 1 divided by tan x right here. So lots of crazy trig identities of functions that you hardly ever use right here. So our first term is gonna be of the form coth right here. And so when we multiply out this bracket, we get all of the prefactors at the start. But of course, cosh divided by shine is going to be coth. And so let's carry on writing our prefactors. And then we're going to get coth of our argument right here that we had. So there we go, there's our first term. But for our second term, we're going to get something even simpler happening, because of course we have a shine right here and we have a shine right here in the denominator. And so these two shines, they're of the exact same argument, and so therefore they're just going to cancel. And so all that's going to be left in the second term is we're just going to have all of the pre-factory stuff right here. So no trigonometric hyperbolic nonsense right here. It's just going to be all of the factors simply multiplied together. And so we're going to get this right here. So there we go. We've got this a little bit simpler, but we can now make masses more simplifications because a bunch of stuff is going to cancel out in both terms right here. So what we're going to find is that the m in the denominator is going to cancel with one of the m's in the numerator. The b's are going to cancel right here. The t's are going to cancel. The kb's are going to cancel. The 2's are going to cancel. So we literally just have m right here as our multiplying factor for this coth function. So what about the second term? Well, the 2's are going to go. One of the kb's is going to go. So if we just take apart the squared function right here, we still have a kbt because that was squared. This was m squared b squared. So the m squareds are going to go. We're going to end up with a 1 over b right here. So this b is going to cancel right here. But what's actually helpful to do is just to divide this by m and multiply it by m again. So this is all the same. Did a lot of cancellations quite speedily there. But I hope you can see that this is what we have ended up with right here. So rewriting this out, we simply get this factor of m times coth mb over kbt minus kbt divided by mb right here. So we've ended up with this much simplified expression. We've still got this coth thing to deal with right here. But thankfully it's way nicer than it was before, and so this is our average magnetic dipole moment in the z direction right here. And so therefore we can write that the magnetization is equal to just n multiplied by all of this stuff right here, because of course it was just n multiplied by the average dipole moment in the z direction. So this is our kind of accurate expression, if you like, for the magnetization right here. What we can actually find is that we can take a couple of approximations. Now, we have this argument mb over kbt right here. And that what we find is that if this argument is small, so if mb over kbt is small, and the way in which we say that it's small is we say that it's much, much less than 1 right here, this must mean that mb is much, much less than kbt. So this is kind of what's going on in the large temperature limit, and this is actually the quite dominant governing behavior for how the magnetization depends on temperature. And so in this regime, what you actually find is that you can expand out this coth minus 1 over, because of course this is just coth x minus 1 over x, where x is just the argument inside the bracket right here. And so when you expand out this function right here, you get that coth x minus 1 over x is approximately equal to x divided by 3 right here. And this is what happens when x is small. So you can actually write that the magnetization is simply equal to n times m squared b divided by 3 kbt right here, we can say that B is equal to mu naught H in this limit right here. And so therefore we can write the magnetization as this. And so our final step is we are going to take the ratio of M divided by H, which is equal to the magnetic susceptibility. And we get that this is equal to mu naught times N M squared divided by 3 kBt. And the critical thing here is that it is inversely proportional to temperature. So this is telling us that the magnetic susceptibility right here, and this is quantifying kind of how magnetic the material is, this is inversely proportional to temperature. And this right here is known as Curie's law. And whenever you have a 1 over T dependence, this is essentially giving us Curie's law, and this applies for paramagnetic materials, and it applies within the majority of temperatures other than those that are really, really cold right here. So there we go. That was Curie's law, and it governs paramagnetic materials. And that is the second form of magnetism that I wanted to cover in this electromagnetism course. And just to reiterate, ferromagnetism is something which I have covered in my video about phase transitions. So if you're wondering about ferromagnetism, I recommend going to that video. So I really hope that was helpful, and I will see you guys in the next video. Take care.